everybody to show up. Okay, so here's our next section. We're going to talk about some different types of chemical reactions, and you guys are probably familiar with these. The two names are known as reduction and oxidation, and I doubt you know those words, although you might, but I promise you, you know the concept. Okay? Oxidation is basically rusting. You guys know what rusting is? It's like when you leave a piece of metal outside in the rain, and what ends up happening is it starts to like deteriorate, and like the outer surface that used to be a nice strong metal, it starts to get really flaky. You can start like flaking away at it, right? You have like a rusty old Chev, and like it's still metal, but like it's breaking down in a way, but like the metal is breaking down. The metal is deteriorating. That's probably the best word I can use for oxidation. So you guys can probably write that down here. Oxidation is known as rusting, which is basically like the deterioration. That's okay word to use. You guys know that word? Deterioration of metal. As it basically like flakes off. That's what oxidation is. Rusting. Well, if oxidation is the deterioration of metal as it like, oh, erosion is maybe a good word to use too, like as it erodes. You guys know the word erosion? Same concept, right? Well, if I told you that reduction is the opposite, what would that mean to you? If something is flaking away and like decomposing, what's the opposite of like something that just like flakes away and decomposes? Yeah, builds up. Yeah. Reduction is like the building up of metal. Uh, the word that we often use, I'm running out of room up here, but the word refining. You've probably heard that before. It's not as relevant in Alberta because Alberta's industry is more like oil and gas. But I grew up in BC, and there's a lot of mines in BC, like silver mines or zinc mines. And really, their goal there is to try to find metal and refine it into something pure, right? You don't just find a metal in the ground that's like all perfect and shiny and ready to turn into a spoon, I don't know, a sword, right? You actually have to like do some chemical processes to it to like purify it. Does that make sense? Refining is the word we then use. So these are words that I know you guys get the concept. I'm pretty sure you have the concept of because you've heard these words before. I just have to teach you like the chemical definitions of these. So reduction, therefore, is the building up of metal and refining something pure, whereas oxidation is like where it rusts and erodes and deteriorates. And really, doesn't that make sense? Don't those seem like the opposites of each other? So let me get to the words we want to use here. We're going to talk about something called a redox reaction. And redox is basically those two words I just described. They're shoved together. There's the RED from reduction and the O from oxidation. And basically, there's a lot of chemical reactions where both of these things happen simultaneously, where you end up having something building up of metal and something losing. You might have heard this concept before. There's something called the law of conservation of mass. Anyone ever heard that phrase before? Right. If something is going to gain mass, it doesn't just randomly get bigger without something else losing mass. So that's why these two things go hand in hand. If something is going to rust away and lose its mass, somebody else better gain. And vice versa, right? If someone is going to get bigger and get built up, somebody else better lose. So now, the reason why they do this at like a molecular level is all about electrons. So a quick little revision of bonds and how that works. It's been a little while. Do you guys need more highlighters or something? You're searching for stuff. What do you need? Here, I got two here. I won't throw them at you. Okay. If you guys recall, bonds work something like this. I'm just gonna do a little recap here. Don't worry about writing this down. But if I were to draw like the energy levels, the first energy level has 2 electrons, the next one has 8 electrons, the next one has 8 electrons. If I were to pick, say, sodium, sodium has 11 protons, and therefore it should have 2 electrons here, 8 electrons here, that gives us 10, and it should have had 1 electron there for 11. But does it like to have just that extra 1 electron just sitting there? No. So it tries to lose this electron. It likes to give it away, and it wants to get rid of that guy. Simultaneously, Oh, by the way, that's why sodium becomes positive. Simultaneously, something like chlorine, which is supposed to have 17 protons, if I were to draw out like its pattern, it would have 2, add 8, that gets you to 10. 7 more is almost full, but it's 7 out of 8. See how this guy right here is almost got all the electrons it needs? So this guy really right here, he needs an electron. Well, where in the world will he find an electron? This guy. Right? And sometimes I give an analogy of like you go to the cafeteria, you want to buy something. The math's a little different. You know how Blair specials are $6? Imagine they're 8. Okay. I have one extra dollar, and you have $7. You don't quite have enough money to buy a special. And I could buy a chocolate bar, sure, fine, right? Or I could just be really nice and say, here, have my extra dollar. Now you have 7 plus 1, you have 8. And that's really what happens in a bond. This guy's electron, this guy over here takes the electron, and now he has all 8, and now he's kind of content and full. And that creates a bond. Well, that's really what happens in a lot of chemical reactions then, is somebody is going to gain electrons, and someone is going to lose electrons. Does that make sense? And in doing so, that's how our matter kind of sticks together in bonds. So that's where my definitions comes from here is when one substance has to lose electrons, something else better gain electrons. Okay? And what we're going to focus on is trying to recognize how electrons are either being gained or lost in different chemical equations. So why don't I hop to an example, because I'm pretty sure I have an example on, you know what, why don't I do, can you guys slip ahead here? Can you guys find this slide here? I know it's not the next one in order, but I think this one is useful to us right now. So can you guys find this one? Okay. Do you need my key to get in the back there? Probably. Where's my key? It's open? Okay. Darian and Rebecca have my keys anyways. So, okay. This is actually the typical equation for rusting. Okay. What ends up happening when something rusts is a metal will react with oxygen, and it will form this chemical here. This is a compound of iron and oxide. This is called iron 2 oxide. Now, iron by itself, nice and strong. But when it turns into this, you guys have seen rusting before, right? It's that like reddish, orangey kind of looking thing where it like flakes off. Right? That's this right here. This is that flaky flakes of like red, orange color. My wife always leaves bobby pins in the shower, and then when the water comes over the bobby pins, anyone seen this happen before? Then it leaves that kind of like that shape of a bobby pin sitting on the bottom. Anyone have sisters, or you're nodding? You know what this is like? Okay, yeah, that's what you're seeing right here. This iron oxide, as the metal literally is deteriorating. Okay, now what I want to focus on here though is charges. Okay. You guys remember how there's different charges? Like say oxygen has a certain charge. What is oxygen's charge? You guys have a table nearby? 2 negative, yeah. And so right here, this is going to be, I'll call it -2, same difference. Iron actually has 2 different charges. What are the charges of iron that are possible? You remember? 2 or 3, yeah. Now in this example right here, it better be +3. It's the only way it really makes sense. And you guys have done this before, right? Because really 2 3s makes a 6, and 3 2s makes a 6. It fits. Okay. What I want to show you guys here, though, is that someone is gaining and losing electrons. And then the charges will help us figure that out. If this thing right here is a metal, you know how when I was originally doing this example back here, I told you that if there's 11 protons, you better have 11 electrons? Neutral atoms have equal protons and electrons. Only ions have charge. Do you guys recall that? Atoms are neutral, ions have charge. So because of that, this iron atom right here should really have a charge of 0. There's no charge to it. It's an atom. And this oxygen right here is also like in its atomic form. It also has a charge of 0. So here's where this comes in then. If someone is going to gain some electrons, someone else better lose them. If oxygen goes from, say, being 0 to -2, if you go from being a 0 to being negative, did you gain or lose electrons? Actually, you gained electrons. And I know it seems like it should be lost, because almost everybody says it at first, but what's the charge of electrons? Are electrons positive or negative? Electrons are negative. So if you become more negative, you must be gaining negative stuff. Does that make sense? So to go from 0 to being negative, you must have gained 2 electrons. Well, based on that same logic right here, how do you go from a 0 to a positive? You actually lose electrons. Can you gain protons? Can anyone explain to me why you can't gain protons? It changes who you are. Hydrogen has 1 proton. Helium has 2 protons. We literally define our chemicals based on how many protons they are. So you cannot gain protons. This is not allowed. If iron gained protons, it would not be iron anymore. It would now be nickel or cobalt or something. You know what I'm saying here? But what you can do is change your electrons. So if you go from 0 to -2, you now have more negatives. It means you gained electrons. But if you go from 0 to positive, you can't gain positive stuff. But you know what you can do? You can lose negative stuff. I know that seems kind of like a double negative, but like if you lose a negative, isn't that kind of like the same thing as like gaining positives? You know what I mean? Like double negatives. Don't not do something means to actually do that. So if you lose electrons, it means you're going down by your negatives, so it actually makes you positive. I guess the point I'm trying to make here is that as you look at these numbers right here, this guy went from 0 to plus. By that logic, he then lost some electrons. And this guy went here from 0 to negative, he then gained electrons. And when we talk about the reactions we're going to do today, someone always has to gain electrons, someone always has to lose electrons. Does that make a little bit of sense so far? I kind of jumped out of order, so maybe I should go back to my slides that I intended, and I'll come back to this. Okay, I'm going to do a little bit of a history lesson for the next couple slides. Scientists have known how to either rust a metal or how to make a metal for like thousands of years. Okay, if you guys can kind of just envision just the idea of like 3,000 years ago, 2,000 years ago, if people were to be fighting, they didn't have guns, they didn't have nuclear warheads. What would you fight with, like say a couple thousand years ago? Yeah, probably a sword, right? No, I mean before that it might have been rocks and sticks or bows and arrows, but like at a certain point, really, humankind's technology really revolved sometimes around the metals they used. Have you guys ever heard of like the phrase the Stone Age? Or maybe like the Bronze Age? Ever heard that phrase before? Or like as humans learned how to make newer and better metals, it advanced society. Now, often it was due to war, right? If I was fighting with a stick and you were fighting with a sword beats stick, right? But eventually, if I'm fighting with a sword made out of iron, but you're fighting with a sword made out of steel, well, now your weaponry is better than mine. You get what I'm saying? Now, but it doesn't just apply to that. Like, say, farming would be another good example. If you wanted to plow your field thousands of years ago, you might hook up an oxen and have, like, him drag a big rock behind you, right? But eventually, we started making gardening tools, like, say, a shovel or, like, a rake or a hoe of some kind, right? And if you make it out of the right metal, well, now that helps advance your society. You get what I'm saying here? My point being is that we've known about how to use metals from their ores for years. And so I want to talk about this term ore. An ore is an impure metal. I'd like to give you guys some examples. One of the most common ores that I know of is this one here. It's Al2O3. This is called bauxite. If you were mining for aluminum, this is what you would mine out of the ground. But the problem is that this is impure. And so you, as the 2,000 year ago scientist who wants to make a shovel out of aluminum, need to turn this aluminum metal into just like good old regular aluminum. What you really want to do is get rid of the compound part of it. I'll give you another example. When you go to a mine and you mine silver, you probably mine silver like this, Ag2O. Now, that's not the silver that you put into like a ring or a piece of jewelry, but this is what you find in the ground, again, as an impure metal or as an ore. You have to then refine it. I'll even write that here. You have to refine it into just good old pure silver. Does that make sense what I'm saying here? So this has been going on for thousands of years. The idea of like purifying our metals out of an ore into something, I don't know, pure. What do you guys notice in common between the two ores I gave you? Yeah, they both involve oxygen. And that's actually a unique thing is that many ores, like say copper usually gets refined in the same process. You take an oxide of copper and you try to turn it into copper by itself. And so I've got a slide that's going to talk about this in a little bit here, but that's basically the concept. Extract a metal, a pure metal, from an ore. And I've got kind of like a timeline here of like the idea. Now, I don't even know it's fair to call them scientists, but like 2,000 years ago, you know how they did this? They just heated them. And if I could give you the example I just had here, don't change it, but you know what happens when you heat this is it basically it melts it, right? And what ends up happening is the aluminum turns into like liquid aluminum, and then this oxygen right here spills off as oxygen gas. And then eventually they put this liquid aluminum into a mold. You'd mold it into the shape of like a sword, and once it cools back down into like solid metal, now you have a sword, right? We used to have like literally like the entire profession based on this. If you worked in swords, you would be or like a blacksmith. Does that make sense? Where like your whole job was to heat up metals, forge them in the furnace, have a kiln or something like that, right? You'd hammer them with like your hammer to kind of flatten them out. You know what I'm talking about here? Cool. Okay, let's move on. Basically, my point then is that eventually by heating them, they could make special metals here, and eventually you go from like the Copper Age to the Bronze Age to the Brass Age, and as time went on, we got better at making our metals, and with better metals, we could do more stuff. Right? Nowadays, the most strong metal that we make things out of is steel. Right? And we even do better. We do stainless steel. You guys know what makes stainless steel so special? It doesn't rust. Yeah. Yeah, it's supposed to be impervious to rusting. Now, I mean, you scratch it or you ruin it a little bit. That's one thing, but So, okay, let me go to my examples of some equations here. These are some examples of reducing equations. And the concept I just described here, the idea of making a metal pure, it became known as reduction. That's where the word came from. You want to purify a metal, means you reduce it. And here's why. You see how this guy right here was Fe2O3? What do we not want out of the Fe and the O? Yeah, so hence the name reduction meant to let's get rid of that. You guys see where the name reduce comes from? Is like we have the Fe, we have the O, but we don't want the O part of it. We just want pure Fe, or we just want pure Sn, or we just want pure Cu. So these would be known as your ores that you mine in the ground, and this is through the process of reducing, you get something pure, and then those pure metals, then you can make something out of them. So, okay, today's lesson is a lot of terminology. I need you guys, when we're done today, to know the words I'm talking about. Because I'm not really going to teach you anything that you need to do. There's really no, like, at the end of today's class, I can't really give you an assignment and say, here, try these questions. But I'm hoping by the end of today, if I talk to you about vocabulary, and I say, talk to me about what reduction means, now you know reduction means take something that is a compound, hack it in half, and purify it into like an element. Okay. Which is where this word comes in, or these two words. I need you guys to know what a reducing agent is. A reducing agent is the species or the thing that causes something else to reduce. These ores right here are about to reduce into something pure. Let me highlight the reducing agents for you. The reducing agents were these things here. Let me explain why. Iron ore by itself would literally sit there and do nothing. But add some CO to it, now a chemical reaction takes place. Therefore, this thing right here is called a reducing agent. It is the agent that caused that guy to reduce. Does that concept make sense at all? So, who is being reduced? These compounds right here, they are being reduced from these compounds to these pure things over here. Why are they being reduced though? They're being reduced because of the pink things I've highlighted, called reducing agents. Reducing agents don't reduce. Reducing agents cause somebody else to reduce. Let me give you a different example. Caleb's really struggling. Sorry, I'm going to pick on you here. He's struggling. He needs some help. He is going to have to be the one to eventually go find a job, maybe. But on his own, he's just too lazy to go find his job. But his good buddy Zach, good friend, he goes off to the store and he says, hey, my buddy needs a job. Can you hook him up with a job, right? Now, who's the one who actually goes to go to work? You're going to work. But you were the agent who caused it to happen. Does that make sense? I don't know. That was a silly example, right? So, you guys know how like an agent in sports is like your representative? I guess that's where I'm trying to go here is that you helped find him a job, so you get reduced, but you're the reducing agent. In this example here, this ore is actually going to turn into something pure, but these guys are the reason why. Did I explain that well enough? Like I said, today's mostly vocabulary. You don't need to do anything, you just need to know what I'm saying. Okay, now the opposite of reduction then is oxidation. So if reduction means take a metal and make it pure, then oxidize means take something that was pure and rust it up, right? Make it impure. And this is one of the best examples, the one I already started with here, where this iron right here, see how this iron was nice and pure, and all of a sudden now it's back to being like a compound, right? If we went this direction here, we call it oxidation. But if we could go back to where we started, you'd call it reduction. See how it's like the opposites of each other? So now one of the best ways of figuring this out is it has to do with electrons. In order for somebody to become reduced, it usually needs to gain electrons. And somebody else needs to lose electrons. That's why I was using these numbers on top here, to try to figure out like how charges changed place. Because as something went from 0 to +3, there's two ways you become more positive. You either gain more positives. You can't. If you gain more protons, you're somebody else. So you can't gain protons. What you can do is lose electrons. So this iron right here is losing its electrons. Well, hey, iron can't just randomly lose electrons. Someone else better take them. Who takes the electrons? Oxygen. Because look, oxygen went from 0 to -2. Now, you were right with your first thought, right? Like, it seems like you should actually be losing, but because electrons are negative, if you become more negative, you're actually gaining electrons. So once you wrap your head around that, then hopefully you can see that this guy gained electrons, and this guy lost electrons. And that's kind of what I want to show you guys today, is being able to recognize how that works. Here's some more examples, by the way, of oxidation taking place. What you guys will notice here is that everything here started as a pure metal and has now turned into a compound. Or another way we could call it is an ore, like O-R-E, like a metal ore. This is basically rusting. Just so you guys are aware, rusting usually specifically refers to iron. So the catch-all term for this is actually known as oxidation. Now, one of the reasons why we called it oxidation is that many examples involved this thing needed to be added to oxygen. That's actually where the name oxidation came from. Reduction came from having two parts to it, and you don't want the second one, so you reduce it. Oxidation came from, well, if you add it to oxygen, it oxidizes. And that's actually where this name came from. Oxidizing agents. If these are the pure metals that are turning into compounds or ores, who are the oxidizing agents? Everybody in this column here. Here's the thing, though. We've now since learned it doesn't have to be oxygen. It actually can be chlorine or bromine or many other things that can be your reason why this pure metal rusts. But because so many of the initial ones that were discovered were oxygen, that's why the word became oxidizing agent and oxidation. So I'm going to put my pad away for a second here. I want to now talk about the 4 vocabulary words I want you guys to know. And you guys are more than welcome to write this down in your data booklet here. I need to make sure you guys know these 4 vocabulary words. So here's the first one. I need you to know what reduction is. Reduction. Reduction basically means taking a ore or a compound and finding a way to make it pure. Reduction means taking an ore or a compound and making it pure. And if you want an example, feel free to put an example in. If you were to take, say, like Al2O3 and find a way to turn it into just regular old aluminum, this would be known as reduction. Well, oxidation is the opposite of that. Oxidation is where you take something that once was pure and turn it into a compound. They're like opposites of each other, right? So those are 2 of the words you need to know. Reduction, take a compound, make it pure, reduce it. Oxidation, or like rusting basically, but rusting is specifically iron, but like it's under the general category of oxidation. Oxidation means take it from pure and make it a compound. The other 2 words I need you guys to know are oxidizing agent and reducing agent. This doesn't just happen naturally by itself. This is going to require something else to get it going. Now, I don't know what that something else is, but whatever that something else is, that is known as your reducing agent, and I'll just call it RA to short if that's okay. So whatever this guy combines with, that's your reducing agent. And the same thing happens in oxidation. This aluminum is going to need to add to something to actually react. I don't know what the something is, but whatever that something is, we call it the oxidizing agent. So those are the 4 words you need to know. Oxidizing agent and reducing agents cause something else to oxidize and reduce. Huge vocabulary here. You're going to wrap your head around that. Do you like this better than math? Most people do, but... So one of the tasks I'm going to need you guys to be able to do eventually is if I give you an equation, I need you to be able to recognize where oxidation and reduction takes place. And sometimes it's obvious. Like sometimes you can just look at it and say, oh, look, this just made a pure metal. That's reduction. Or, hey, look, this thing just added to oxygen. Now it's not pure anymore. This is oxidation. So sometimes you'll be able to see it. But one of the things I mentioned is the whole idea of loss and gain of electrons. Because really, electrons are at its core. What do electrons do? They start making metals stick together, right? Remember that idea of sodium and chlorine? Chlorine needs an electron, sodium has one, that causes them to stick together. If we can keep track of electrons, it can actually help us know who these different things are for oxidizing and reducing. Before I get there, I guess I forgot I have a slide here. One of the things I need you guys to be able to do as like a background skill is to be able to balance an equation. Is this equation oxidation or reduction? You got a 1 and 2 shot at it. Is this equation oxidation or reduction? You're right. Can you explain why? Yep, starts off as a pure metal and eventually turned into a compound. Yeah. So in terms of how I would describe this, this is being oxidized, and then these 2 things right here would be your oxidizing agents, because you needed both of these to cause you to turn into you. Come on in, Joe. What's up? Oh. That's okay. Thanks, Joe. Okay, one of the skills I need you guys to have as a background skill before I go any further, though, is when we start talking about equations, I need you to be able to balance equations. So you may have a little bit of practice with this, maybe not. So can I show you guys my technique for balancing? And then if you already know how to balance, like, you can kind of ignore me. But I need you to know how to balance. What I like to do is I like to make a bit of a chart. This is before, this is after. And I try to figure out how many of everything I need. So we're going to need to have some silvers. we're going to need to have some hydrogens, we're going to need to have some sulfurs, and some oxygens. Basically what I just did is I went through the list of all the chemicals involved. Silver, hydrogen, sulfur, oxygen, and then, well, I've already got silver, I've already got sulfur, I've already got hydrogen, I've already got oxygen. This is my technique, by the way. You don't have to use this. Then I make a bit of a chart, and I try to keep track of, well, how many of each do I have? How many silvers do I have before I started? 1. How many silvers do I have after the equal sign, or after the equation has? 2. That's not good. Well, we're going to fix that at some point. I have 2 hydrogens before I start. And over here I have actually 2 hydrogens. So that one does not need fixing. There is 1 sulfur right here. There is 1 sulfur right there. And then the last one is oxygen. There's 2 oxygens here. But there's only 1 sitting right there. So this is kind of my method. So which ones need fixing? Silver and oxygen. So in order to do that, I'm kind of giving you guys the bridge version, but you guys have seen a little bit before that we put like a number beforehand. Is that somewhat familiar? So what I can do is, since these oxygens aren't balanced, I'm going to put a 2 in front of that right there. The reason why is that now I've doubled all of my oxygens. However, as a side effect, I actually also happen to double my hydrogens, because now I have 2 times 2 for 4 hydrogens. Kind of buggered that one up. So then I go look somewhere else and I say, well, then if I need 4 hydrogens, then I guess I probably need to have 2 right here. As if I do that, now I'll have 4 hydrogens. But you know what else it also changes, though, is now I have 2 sulfurs. So I go, okay, well, that's fine. So now I need to fix my sulfurs 2 to 1. So I go over to this guy right here, and I say, well, why don't I put a 2 here? Because what that would do is that would give me twice as many sulfur. But then look at my silver, I'd now have 2 times 2, I'd have 4 silver. And this usually forms a really nice loop when you're done. The only thing I haven't now balanced is my silver. And if I go over here and I just put a 4 in front of silver, now everybody is equal all the way across, and I'm good to go. So I threw this in as a slide because before I go any further, I just need to know that you guys have a little bit of skill in balancing things. Because if it's not balanced, it's not chemically correct. So, that made sense? Okay, moving on then. When we're looking at chemical equations then, there's actually a silly little mnemonic device. You guys know what a mnemonic device is? It's like where you like have like an acronym or something attached to things where like the letters each spell something. So like, I'm trying to think of another good one right now. What was that? That'll work, yeah, Roy G. Biv for the rainbow. Or how about this one? The one for like team. Together, everyone achieves more. TEAM. Something like that. Or like the way the letters come together fits. This is a silly one, but it really works well for helping kids remember what oxidizing and reducing is. It's Leo says gur. Leo is a lion, and lions say gur. It's dumb, but you'll remember it. Okay. The way the acronym works here is that LEO for Leo means loss of electrons. And the way that works is that if anything loses electrons, it is being oxidized. And anything that is gaining electrons is being reduced. And so when we want to look through examples to figure out who's being oxidized or reduced, we can now do that by looking at charges. I want to go back to the previous slide now. So go back to the last slide we just were on. And I'm going to walk you guys through how to look at charges to figure out how someone was oxidized. Remember how we said a second ago that something was oxidized? What was being oxidized specifically? Silver. Let me prove it to you. Over here, in this compound over here, silver's in a compound. What is the charge of sulfur on your table? You'll have to look it up on your periodic table if you can't see on that one. If you can see on that one, that works. But what's sulfur's charge? 2 negative. Okay. So sulfur is 2 negative. Anybody know this charge of silver? Again, you just need your table out. Positive 1. You guys know where to find this, right? Okay. Well, that's because these guys were in an ionic compound. They were combined together as a compound. Over here, though, silver is by itself as an element. What's the charge of elements, atoms that are neutral? 0, yeah. Okay, so now what I want to do is I want to talk about silver. Silver went from 0 to +1. Now, there's two things that could happen here. Either you become more positive. That's not actually allowed, though. So if you're not becoming more positive, you must be becoming less negative, which means you must have lost electrons. If you can follow that logic here, to go from a 0 to a +1, you must have lost one of your negatives. If you lose a negative, then there must be more net positives left over. And that's where this little acronym comes in. Leo says GER. Loss of electrons means you are, boom, oxidized. Now, we knew it was oxidized anyways because we could see that it went from an element to a compound. But an alternate way of figuring this out is to look at the charges that are above things and recognize that as the charges change, that helps us figure out who changes as well. That makes sense at all? Now, one more thing though. If this guy right here lost electrons, someone else better gain them. Because you can't just randomly lose electrons. Someone else better gain. So I'm actually going to keep going. I'm going to find some more numbers for different charges as we go along. So let me do oxygen and hydrogen here. What is hydrogen's charge? +1, yeah. And what's oxygen's charge? Good. Now, you guys are saying this. Everybody okay with knowing how to find that? Okay, moving on. Here, oxygen is an element. It's by itself. It's not in a compound. Elements are 0. Well, look at this then. See how oxygen went from 0 to -2? If you go from 0 to -2, you became more negative, which must mean that you must have gained electrons, which is good, because if we a second ago said that silver lost electrons, it means that somebody else better gain electrons. Who gained the electrons? Oxygen gained electrons. You always have to have a doppelganger. You can't just have one, you have to have both. Here's what that means then. According to Leo says GER, anyone who gains electrons is reduced. So therefore, it's actually fair to say that oxygen was reduced and silver was oxidized. Now, for the most part here, like, no one cares that oxygen gets reduced. We normally just care that silver gets oxidized because we just went from having pure silver to something that's not pure. It's not valuable anymore, right? This has now been tarnished. So we usually don't care about the other side, but I need you guys to know they both exist. This is basically the core of my lesson. If you guys can take a chemical equation and identify for me who gets oxidized and reduced in all this vocabulary, then today was successful. So let me show you guys some more examples here, basically, just to kind of solidify this. See how this metal atom right here is like turning into like an ion? The reason why it's doing that is because it must be like losing some electrons. Or you could have that happen even from this one here. Here I've got something that actually has like a negative charge, and it went from -1 to 0. How do you go from -1 to 0? You must have lost an electron. How do you get from 0 to +2? Lose electrons. How do you get from +2 to +3? Lose electrons. Anytime the number goes up, you're losing electrons. Anytime it goes down, you're gaining electrons. Here's the opposite. See how this guy's going from nothing to -1? How do you go from nothing down to -1? Gain electrons. How do you go from +1 to 0? Gain electrons. How do you go from +3 to +2? Gain electrons. So if you can figure out charges of things, you can then figure out who gains or loses. And then using that really silly mnemonic, Leo says GER, it can help you figure out which is which. I think I have some examples, and then we're going to call her quits. Oh, yeah, okay. Can we go to the very, very last slide? Let me go there, and then I know I've skipped a bunch of stuff. I'll come back to it as we need to, but why don't I go to like the final product? Now that I've taught you guys a lot of stuff, this is what I need you to be able to do. If I give you some equations, we need to figure out what is happening. So I'm going to write out the first one a little bit bigger just because there's not a lot of room here. You guys might need to just squish it in there or maybe rewrite it as well. But I'm going to rewrite it as zinc solid adds to 2 HCl's. It's going to turn into zinc, and I'll have to write it down here, hydrogen like that. Our goal is to figure out the following 4 things. We need to figure out who is being oxidized. We need to figure out who is being reduced. We need to figure out the oxidizing agent and the reducing agent. Those main 4 things I focused on before. So sometimes it's obvious. Sometimes it's not as obvious. So one of the best ways of doing it is to try to figure out their charges. What's the charge of zinc going to be when it's just by itself? 0. Yeah. Oh, you guys probably can't see yellow, can you? That's not very good. Let's change that. Let's go to green. 0. Oh wait, what are the charges on H and Cl? So you just got to go to your table. Hydrogen's got a charge of 1 plus. Chlorine's got a charge of just a negative. Okay. That makes sense, right? 1 plus and 1 minus, they fit together. What about zinc and chlorine? We just looked up chlorine, right? Chlorine is -1. What's zinc's charge? Perfect. And doesn't that make sense that you'd have to have 2 -1s to match a +2? And then finally, what is hydrogen's charge going to be, but not in a compound, by itself, as a pure element? 0. Is able to follow that a little bit so far? Okay. Now we got to figure out which numbers changed. I think zinc changed, didn't it? See how zinc went from 0 to +2? Okay, it went up in number. Did it gain or lose electrons if it went up in number? You're right. Good. It takes a while to wrap your head around that, but if it goes up in number, this guy must have lost electrons. So according to our little silly Leo says GR acronym, loss of electrons means that this thing right here is oxidized. And I can now label that. What was being oxidized? Zinc was being oxidized. And honestly, I think I knew that anyways. Because wasn't zinc starting off as pure and then turning into some sort of compound? Wasn't that what we learned what oxidation was anyways? Cool. But here's the thing, there always has to be a doppelganger, even if we don't care about it as much. Because it's probably the zinc we care about, but there better be someone who lost electrons. So I'll use another color pen here. Who had a number change the other way? I think it's hydrogen, right? See how H went from +1 to 0? So if you're going to go from +1 down to 0, you gained electrons. Yeah, it takes a while, but once you wrap your head around that, this guy gained electrons. And according to the silly little acronym of Leo says GR, gain of electrons means that this thing was reduced. More specifically, though, if I were to ask you who was oxidized, you would say it was zinc. And if I were to ask you who was the reduced, the other half of it, you would actually just say hydrogen. Because the chlorine, did the chlorine actually change its number at all? No. We have a name for that in chemistry, not that I need you guys to know this, but it's called a spectator ion, if you ever get that far in chemistry. Now, there's still 2 more things I want you guys to be able to label, though. We also need to be able to label the oxidizing agent and the reducing agent. Because oxidation doesn't help unless his buddy gets him going, right? Zach doesn't have a job in this example, or Caleb doesn't have a job unless Zach went out and got him one, because he's his agent, right? So if zinc was being oxidized, who's the oxidizing agent? This guy got oxidized. This thing right here is the oxidizing agent. So the entire HCl is the oxidizing agent, causing zinc to be oxidized. Okay. As a general note here, when we ask about who's being oxidized and reduced, we talk about just which atom. When we talk about the agents, though, we talk about the entire thing. So I know chlorine had no role in it, but in this case right here, I got to talk about the whole piece. And then for the other one, the guy who was reduced was hydrogen, right? But who caused hydrogen to get reduced? Zinc. So the zinc is the reducing agent. If you guys can do this by the end of my lesson here today, we're doing great. So out of curiosity, how am I doing? Does this make sense? Cool. Okay. I'm taking her slow. I know I've got a little extra time here, but why don't I do one more example? Why don't I go back then and do the notes I skipped, and then I'll have you guys take a look at a couple. But do you guys get what I'm saying here? We're like, there's no work to this, right? It literally is like a just look at it and tell me what the answer is. You may write a little bit of notes like I'm doing right here, but like honestly, after a little while, you won't even write those. So why don't I do one more, just example off of here, and then I'll do the notes I skipped. Let's just do the second one, I guess. I just have to rewrite it out here. It was 3 MnO2s, 4 aluminums, 3 Mns, and 2 Al2O3s. Okay. So I'm going to start with the exact same process. I'm going to start by writing out some numbers of charges, because the charges really helps get me going. So, two of them are actually really easy. Aluminum and this manganese right here are zeros because they're by themselves. The other ones are a bit more challenging. Anyone know what aluminum's charge is? Yep. And oxygen? Nice, cool. And hopefully that like makes sense, doesn't it? Because there's a 2 here and a 3 there, like that. That's kind of how it fits. Over here, oxygen's -2. I don't know what your table says. What does it say for Mn? It's manganese. Does it give more than one charge for manganese? Okay. And since there's 2 possibilities, does it make sense to you guys that it has to be the +4? Because you need to have 2 -2s, which would give you a net of +4 or -4, which means the manganese better be +4. So because you have 2 -2s, so each oxygen brings a -2. 2 -2s gives a net of -4, which means your manganese to balance better be +4 for it to fit. So if you're okay with that logic, then now we have enough to use that silly little Leo says Gur bit. So again, you won't write this out every single time. I need you to be able to figure out who gets reduced, who gets oxidized, who the reducing agent is, and who the oxidizing agent is. Those are the 4 things I would ask of you. So I'm going to start. I like to draw it like this. I'm going to say manganese is going from a 4 to a 0. 4 to 0. Are you losing or gaining electrons? Right, yeah. Gaining electrons. So according to the Gur, it must be reduction must be Mn. Manganese is getting reduced, which honestly I knew that anyways. Because look, here it was in a compound form, and here it is pure. Wasn't that the definition of reduction? Okay, then we got to figure out oxidation. Here the aluminum went from 0 to 3. If you're going to go from 0 to 3, you lost electrons, yeah. It takes a little while to wrap your head around that, but once you do, it's not so bad. So according to the silly little mnemonic Leo says Gur, loss of electrons is oxidation, so aluminum must have lost electrons. Oxygen, by the way, did nothing. That's okay. Not everything has to be involved. Also, by the way, doesn't this make sense? Aluminum went from being pure to being a compound. Wasn't that the definition of oxidizing? Isn't that rusting, basically? And then the last thing, and these like always seem backwards, but if this guy right here was, like loss of electrons is oxidized, then this guy is the oxidizing agent because it caused that guy to oxidize. So therefore, your oxidizing agent is the MnO2. And if this guy gained to reduce, then the agent that caused the reducing would be this one. It's almost always backwards, basically. Yeah. I lost that, hey? Okay. So first I just want to make sure that we're clear that aluminum, you said it lost electrons, right? According to Leo, loss of electrons means this guy is oxidized. Okay. Why did this guy become oxidized? Who was his agent that helped him? This guy was the oxidizing agent that helped this guy become oxidized. In my silly analogy here, that's where this is Calum needing to have a job. His agent who advocated for him and got the contract all lined up, which was Zach, This is Zach getting aluminum the work he needs. I don't know. That's my analogy. It seems backwards, right? Because like this is the guy that is oxidized, and so just like I said, Caleb has to actually be the one to go to work, but this is his agent that got him going. Because this reaction, by the way, here, aluminum to aluminum oxide, would not happen unless you had this stuff. You have to have this one too. Conversely, the color here, we said a while ago that this manganate right here gained electrons, and gain of electrons is reduction. So this guy is being reduced. Why is he being reduced? This to here would not have happened on its own. It only happened because aluminum was this guy's agent. So aluminum is the reducing agent. So the reducing agent is aluminum. The oxidizing agent is MnO2. If you guys can do that, well, we had a good day then. Does that make sense to you? This is one of those things where like the more we do it, probably get the hang of it because it's like pure 100% vocab. Okay, I'll leave the rest of these examples if that's okay. You guys can try them on your own a little bit later if you really want to for practice. Why don't I do the sides I skipped and then we'll call it a day. So I think this is about where I left off, right around here. Oh, actually no, it was this slide right here. There was an example here that I skipped because I went to the more harder one. But I think I can skip this one because you guys seem to get the concept here. Like if something goes from a 0 to a 4 plus, gain or lose electrons. Lose. Whereas something goes from a 2 to a 3, lose. But if it goes from a 4 to a 2, gain. Okay. I feel like you guys have. I skipped over this one because I got the impression you have this down as a group. So let me go to my terminology slides here. Oxidizing agents then, like I just said, oxidizing agents is the other thing in the equation. Okay? If from here to here oxidizes, this guy is the oxidizing agent. Let me just draw this out again. If you have A plus B turns into C plus D, if this thing right here is undergoing the loss of electrons to oxidize, you are the oxidizing agent. The opposite one is. And then the same thing happens here. If you have A plus B turns into C plus D, and what did I do last time? I did A. So if B going to D, if this is the gain of electrons to be reduced, then you're the reducing agent right here. So it seems weird because it's like opposite, but once you wrap your head around it, it's actually pretty easy once you wrap your head. Okay. What else do we need to cover here? This is just the acronym again. Oxidizing agents and reducing agents, so you get the hang of this. The real key, I guess, to this is you just have to figure out who loses and gains electrons. If you can kind of label the +2, +3, -2, 0 sort of stuff, that's really the trick to getting this going. Here's a picture kind of format of it. We're going to do some lab work on this. Here's an example, a really common one, of copper and silver nitrate going to copper, nitrate, and silver. And I'll breeze through this because I feel like you guys have the hang of this. Here, copper is going from 0 to a +2. And here, silver is going from a +1 to a 0. And so you can actually kind of see once you get the hang of it that this guy right here must have, let's see if it goes up, it must have lost electrons and become oxidized. And this one right here must have gained electrons and become reduced. No. And so what we can actually do is we can just write it out in halves. We can say, really, this copper went from the 0 format to the +2 format. And I can kind of skip out writing the other stuff there. Because that stuff that I wrote out behind there, it really didn't matter that it was nitrate. Like, it didn't do anything. And so sometimes what we'll do is we'll skip writing that out. And we'll just do like just portions of it. I'll color code it. We're just going to say that this copper went to the copper 2 plus, like I have right here. And the reason why I did that is that this lost electrons. Any electrons on the like product side have not been lost. But if someone's going to lose electrons, someone else better gain them. Because here a +1 silver turned into 0 version silver. And in order for it to do that, hey, this is the guy that gained the electron. So any electrons on this side of the equation have been gained. Any electrons on this side have been lost. But like, I don't know, this didn't really add anything new to what we've been talking about. Not that much. You know what? I think I've covered what I needed to. Can we try one last example? Can I maybe have you guys try one without me doing it, and then we'll call her a day? Because this is my last slide, right? Yeah. Why don't we try? Let's try C. I'll erase all this. You guys take a few seconds to try C by yourselves, and then we'll call her a day. So here's the 4 things I need from you. In the equation, 2Al plus 3I2 goes to 2AlI3. I need you to tell me who is being reduced, who is being oxidized, who the oxidizing agent is, and the reducing agent is. And I gotta be honest, you've got like a 1 in 2 shot of getting it right anyways, right? Like, it's not like there's a lot of choices here. Like, sulfur is not being oxidized, right? It's either aluminum or iodide. Anyways, take a try at it. So I don't want to spoil it if you haven't finished yet, but why don't I jump in here? Aluminum is by itself, that's a 0, and iodide is by itself, that's a 0. Sometimes kids forget that. They forget to just use the natural element ones as zeros. So now you need to look up aluminum and iodide's charges in your table. Hopefully you can do that. It's +3 and -1. So that should have been step 1, hopefully. Next step. We got to figure out who goes up and who goes down. So I'll just start with aluminum. Aluminum went from 0 to +3. If you go up in positiveness, it must be because you lost electrons. It's probably the hardest thing for kids to wrap their mind around, because you're like, hang on, you went up, didn't you gain something? But like, you can't gain positives. All you can do is lose negatives. So just lost this. Loss of electrons, according to like the Leo saying GER little acronym, loss of electrons means that aluminum is oxidized. And if aluminum is being oxidized, the oxidizing agent is the opposite one. So the oxidizing agent is your iodide. And then you probably already know you have it right then, right? Iodide went from 1 down to 0, which must have been the gain of electrons. So according to GER, gain of electrons means that iodide was being reduced. You could write it with I too, but it's specifically the iodide itself that's being reduced. There's just 2 of them, which means if iodide is being reduced, aluminum is your reducing agent. There you go. If you can do that, we had a good day. So, we have a good day? Cool. Okay, I'll stop the video. I know it's basically time to go here in the next few minutes, so couple passing thoughts as I turn the video off here.